Hello, everybody. Welcome back. Today we're going to go over section 4.5, which is business applications. Now that we've talked about the derivative and the second derivative and how they relate to and describe aspects of the original function, we can continue on with some application problems. So in this section, in particular, we will talk about how to maximize revenue. And while revenue is the standard revenue equation we learned early on in chapter 2, we're going to build a different structure for the revenue equation. So it's the revenue as we know it. It is the income to a business, selling price times the number of items, but we're going to have to build the revenue function in a different way than what we have been used to previously. And when we want to maximize the revenue, that means that I need to find a local maximum of revenue, which, as we know from chapter 3, maximums and minimums both come from critical numbers. So the gist of these problems in this section will be, let's build the revenue function in a different manner than we've done before, and then let's find its critical numbers that correspond to maximums. And in the same way, we're going to minimize inventory costs. Now, inventory costs is a new function that we have not built yet, so I have to walk you through how to build the inventory cost function, and the formula for that is coming right up. But after we build it, we will have to minimize it. So I'd have to find a local minimum or the critical numbers that correspond to a minimum. So let's get started with these types of application problems. First up, let's look at the general formula for how to create the inventory cost function. Now, the inventory cost is a combination of how much it costs retailers to store their items. So retailers' cost of maintaining an inventory of goods consists of two categories: the storage costs and the ordering costs. How much it costs to store, to keep them on the shelf, and how much it costs to order to replace the items that have been sold. And in this particular breakdown for the inventory cost function, these are the two items that are being considered. And we have some labels here that we're going to make use of. So X is still kind of classified as the number of items, but X is called the lot size. Now, lot size means the number of items that you buy at once. So let's say that you are selling something. Most of the time, you don't buy a whole year's worth of inventory in January and then keep it on the shelf all year. You, over time, make multiple orders a year as time goes on, as the items are being sold. So the lot size is the number of items that you're buying at once. So once a month or once every 2 weeks, whatever it is, how much you're buying each time you make an order is called the lot size. The average number of items in the inventory in general, they are always giving that. We always use for here X, the lot size, divided by 2. And this is a formula we'll use repeatedly. It's what they want us to use for the average number of items. And the number of orders per year is given by the total that you order in a year, specifically, divided by X, the lot size. So we're going to use these terms and have to find like the number of orders per year and things like that when we're working with these formulas. Now, the inventory cost function, that new function I told you we would have to build, is in its worded version given by this. You take the storage cost per item, whatever it is they tell you that is, and you'll be multiplying that by X divided by 2. And then you add this other term that is multiplication of the cost per order, which is, again, you'll know that based on the problem. And you have to multiply that times the total ordered, and that's always per year, divided by X. So we're going to keep this formula on standby because we're going to need it on the next page when we start doing these word problems. Here we go. Let's read practice problem 1 here. Keep that formula on standby. Here it is. There we go. Okay. All right. I've got it. Okay, here's the formula I'm going to need, and here's the word problem it's going to apply to. So we're going to keep that up there. A sporting goods store expects to sell 120 tennis rackets during the next year. It costs $4 to store the tennis racket for 1 year. To reorder, there is a fixed cost of $15 plus $4.70 for each tennis racket you order. In what lot size and how many times per year should an order be placed to minimize inventory costs? So there's a lot to pick out of this, but the key words that we really want to latch on to is the last 3 words, actually. Minimize inventory costs. In particular, they're talking about doing something with an inventory cost function. So that says to me that I have to build the inventory cost function. Now, once I find the inventory cost function, once you build it, you're supposed to minimize it. Now, that's the calculus part. You got to find the critical number of the inventory cost function. For the inventory cost function, I'm going to use this generic formula to help me build it. So let's get started with that. Inventory cost function, which we will write as C, is given by what? It's given by the storage cost per item times X over 2. That's the first term, and then I have to do the rest of it. What's the storage cost per item? So our items this time is given by tennis rackets. And so I'm looking for how much it says that it costs to store my tennis rackets. So they say it costs $4 to store 1 tennis racket for 1 year. So the storage cost is $4 there. $4 times X divided by 2. Now I have to scooch over here to the second term. I have a big plus sign in the middle here. Then it says times the cost per order. Now, how much did they tell me it costs to place an order? It says there's a fixed cost of $15 plus $4.70 for each tennis racket ordered. So if we let X, which X represents the number of items, but in particular, it represents the lot size, the number of items you buy at once. $4.70 for each tennis racket means you're going to have $4.70 times however many items that you place in that order, which would be X, the lot size. Plus, I have a fixed charge of $15. So that's just going to be a flat number that's added on the end. Now, this is supposed to multiply by the total ordered per year divided by X. So this refers to how many tennis rackets will be ordered in 1 year. So if we read the top part, it says the sporting goods store expects to sell 120 during the whole next year. So that's the total order. That would be the 120 over X, and this should be arbitrary, because X is the thing I'm trying to find, right? Now, is that the thing I'm trying to find? Am I trying to find X? Actually, yes, because it says what lot size. So that means what X minimizes inventory costs. So I have to build my inventory cost function, and I need to find the X that corresponds with a local minimum. So this is standard stuff we've actually done in chapter 3, but we're putting a different, a word problem spin on what it means. Now I've got to simplify my inventory cost function if I'm going to do anything useful with it. So let's multiply this 4 times the X over 2. That becomes 4X divided by 2, or 2X. And then this over here, this is a binomial times a monomial. What I'm going to do is multiply that 120 over X times the 15 and times the 470X. Now, since those are clunky numbers, I'm going to write this out. I'm going to have 470X times that 120 over X, and then I'm going to have that 15 times that 120 over X. Let's go ahead and multiply those. So let's see here. I have 4.70 times 120. That'll be a number. But then I have X divided by X. Those will actually cancel each other. So all I'll have left is the 4.7 times the 120. So this is where we're going to get out our calculator here and figure out what that equals. We have 4.7 times 120. So I have a constant here of 564. Then I come over to this term. What's 15 times 120? That says it's 1800. So that'll be 1800 over x there, because here the x doesn't cancel with anything. This is my inventory cost function. Now I haven't done anything with it, but I am supposed to find the minimum of that. Now this is where we have to call back and remember applications out of chapter 3. How do you find a minimum? Well, a local minimum, the x values that may correspond to a minimum or a maximum for that matter, is a critical number. So I need to find the critical numbers of that. And how do you find critical numbers in general? You take the derivative and you set it equal to 0. So I'm going to need to take the derivative of this, which means that I really ought to prep C so that it's a little better suited for taking the derivative. What I'm going to do, and what I mean by that, is I'm going to take this x and flip it up so that this is 1800 x to the negative 1. Now this is in a better form for taking the derivative of. Let's take the derivative of c, find c prime. That way I can set it equal to 0, find my critical number. The derivative of 2x is 2. The derivative of 564 is 0. And then this term here is a power rule. 1800 times negative 1 is minus 1800. X to the minus 1 is negative 2. So this is my derivative. I'm now going to flip this back down into the denominator and make this 1800 over x squared. I'm supposed to take this now and set this equal to 0 because I'm trying to find the critical number. My critical number will correspond to our local minimum. So add the 1800 over x squared. Multiply both sides by x squared. You get 2x squared is equal to 1800. Divide both sides by 2. You get x squared is equal to 900. Now you square root both sides, and we get x is the square root of 900. Now, usually you would have a plus or minus that comes out when you're taking the square root. However, x is representing a number of items, so it doesn't make sense for us to have a negative number of items. That's not something that's possible in the real world. So we only consider the principal positive root because it doesn't make sense to have negative items. What's the square root of 900? It's 30. So that we find that we get one critical number, and it's 30. And these will work out conveniently where this does correspond to the minimum you want. This is your lot size. That's how many tennis rackets you should place in one order. 30. You should order 30 at a time. So then the question is, if I order 30 at a time, how many times per year would I be making an order? So that's the other question it asks. What's the lot size? Well, it's 30. And how many times per year should you make an order? Well, how many do I plan on buying in the year? It's 120. So I'm going to come over here. The number of orders per year, this is kind of where I point here. The number of orders per year is the total I intend on ordering in a year divided by the lot size, how many you're going to buy at once. So our number of orders per year is the 120 tennis rackets that I plan to buy over the year divided by the 30 size lot size. So the number of orders per year is 4. So that is to say that you'll be ordering 30 tennis rackets at a time 4 times a year, so every quarter. And then those are the answers for this problem. The lot size is 30, and you should order 4 times a year to minimize inventory costs. All right, let's do another one. Similar premise, slightly different numbers. It says a bookstore expects to sell 110 textbooks during the next year. It costs $3.75 to store one textbook for 1 year. There's a fixed cost of $8.25 each time we make an order. It says find the lot size and the number of orders per year that minimize inventory costs. So this is the same exact thing that we just did, just with different numbers. They want to know what is the number of items I'll buy at once, X, and the number of orders per year. With that will inventarize the same function, the inventory cost function. So that means that we should build our inventory cost function again, which means that I want to use that generic wordy version that I have from my previous page. So the inventory cost function, you build it. It's the storage cost per item. So our item this time is textbooks. How much did it say that it costs to store your textbooks? It said $3.75. And you would take the storage cost per item times that X divided by 2. It's always going to be X divided by 2. That part will never change. Plus the cost per order. Now the cost per order, it says there's a fixed cost of $8.25. So it didn't say it's $8.25 per book. It just says there's a fixed cost in general of $8.25. So that means there's just going to be an $8.25 flat cost. It won't depend on the number of books or anything. I don't have to multiply by X. The total ordered per year, that's how many I expect to buy throughout the year, or sell throughout the year rather. And they said that would be 110. So you'd have 110 divided by X there. So this is my inventory cost function. Let's simplify it. I'm going to have 3.75 times X divided by 2. So what's 3.75 divided by 2? I get 1.875x plus 8.25 times 110. So let's do that. I get 907.5 divided by x. Now this is my inventory cost function. So if I want to minimize the inventory cost function, I've got to find a critical number of the inventory cost function, which means I want to take the derivative and set it equal to 0, the same things that we had been doing in chapter 3. So let's tinker with this one just a tad by flipping up this x so that my original function is in a little more derivative prepped style. There's my inventory cost function. It's ready for me to take the derivative. Let's take the derivative. The derivative of 1.875x is 1.875. This is a power rule, which would be negative 907.5 x to the negative 2. Now I'm supposed to do what? I'm supposed to set this equal to 0 so I can find my critical number. Now what you should do to make the algebra make more sense is now that you've taken the derivative, you flip this x and put it back down in the denominator. This will be 1.875 minus 907.5 over x squared. Now I'm going to solve for x. Let's take this term and add it to the other side. Multiply both sides by x. Divide both sides by 1.875. So 907.5 divided by 1.875. And I get 484. Now, if you square root that, you get a nice solid value of 22. Now, since we are dealing with a real world problem, we would not worry about the plus or minus square root because it doesn't make sense to have negative 22 items. So we just use the positive case since we're dealing with a word problem here. Now this is going to correspond with my minimum on my inventory cost function. So if I want to minimize my inventory costs, I need to make sure to order a lot size of 22. That is, order 22 items at a time each time that I make an order. So if I'm ordering 22 items per order, how many orders will that end up being? The number of orders is equal to the number of books that you're going to need throughout the year, which is 110, divided by the lot size, how many you're ordering at once. So if you take 110 divided by 22, you get 5. So if we make 5 orders per year, and each time you make an order, you order 22 books, this will minimize the inventory costs. And that's it for this problem. Scooch on over here to number 3. It's very similar again. Says a jewelry store expects to sell 110 bracelets during the next year. It costs $250 to store 1 bracelet for 1 year. To reorder, there is a fixed cost of $550 plus $360 for each bracelet ordered. In what lot size and how many times per year should an order be placed to minimize inventory costs? So we're finding the same thing that we've done for the last couple, and we are minimizing inventory costs again, which means I need to build my inventory cost function again. So let's bring our template back over here and reference it. Here's my word template. I need the storage cost per item. So I'm selling bracelets. What's the storage cost for my bracelets? It says it costs $250 to store 1 bracelet for 1 year. So that means you're going to have 2.50, the storage cost, times x divided by 2. Now we scooch over to the rest of the problem. I need, we have plus the cost per order. So how much does it say it costs to order my bracelets? It says that there's a fixed cost of $550 plus $360 for each bracelet. So I'm going to have $3.6 charged for each bracelet in that lot size that I order. So I'm going to have X here, plus a fixed flat charge of $550. So my cost per order is $360 per bracelet for every bracelet in that lot size, plus $550. And then I have to multiply that by the total number of bracelets I plan on ordering per year, which is 110, divided by X. This is my inventory cost function. Let's clean it up a bit and multiply things through. You have 2.5 times X divided by 2. So you take 2.5 divided by 2. And that's 1.25X. Now I'm going to take, since this is 2 terms here, I'm going to take this 110 over X and multiply it times both of these terms. Let me write that out. It'll be 360X times 110 over X plus 550 times 110 over X. Now, when I have 3.60X times 110 over X, this is X times 1 over X. This is X divided by X. Those will cancel. Now, 3.60 times 110, I'll just have a number that comes out of this term. I get 396. Now this one, I'll have 5.50 times 110. And that is all over that X there. That X. So this is my inventory cost function. And I'm supposed to minimize that, which means I need to find its critical number, which means I need to take the derivative So let's prep this thing real quick. I'm going to take this term and make it look like 605 x to the negative 1. That's a better way of writing that term when I'm about to take the derivative of it. So let's take the derivative. The derivative of 1.25x is 1.25. The derivative of 396 is 0. And the derivative of that is a power rule. We have 605 times negative 1 is negative 605, x to the negative 2. Now that my derivative's done, you should flip that x to the negative 2 back down into the denominator. And then we're going to take this and set it equal to 0 so you can solve for x. Take this term and add it to the other side. Multiply both sides by x squared. Divide both sides by 1.25. 605 divided by 1.25 is 484. And when you square root both sides here, you get x is 22. So this is my lot size. This is how many bracelets you should order at once when you make an order. So if that's how many that you're ordering at once, what's the number of times per year you're going to make that order? That would be how many you expect to order in a year, which is 110, divided by the lot size, which is 5. So to minimize the inventory cost of this one, you need to order 5 times a year. And each time you make an order, you order 22 bracelets. All right, so that concludes our analysis of inventory cost function. Let's go to our other application I mentioned, which was instead of minimizing inventory costs, how about maximizing revenue? So we kind of end that discussion and we want to start a different discussion. Susan knows that she can sell 440 donuts a day at 50 cents per donut. What price should she charge to maximize her revenue if for every 10 cents she increases the price, she sells 40 fewer donuts? And then what would this revenue be? Okay, so they're asking what price, how much should she charge to maximize revenue? Now, the terms that we should really latch onto here is the word maximize revenue, because that tells you exactly what function you're dealing with. That means revenue is the function that we're going to build, and if we're going to maximize it specifically, I want the critical numbers of this thing. I want critical numbers of revenue, which means they'll be taking the derivative of revenue, setting it equal to 0, blah, blah, blah. So I'm dealing with revenue. And revenue, since they didn't give it to me, is something I need to build. And in general, its formula is the same as it always was. Revenue is the selling price times the number of items. Now, the difference is that the number of items isn't X anymore, and they're asking you what is the selling price, which means they're not telling you what the selling price is, not directly. It's changing. So we're going to have expressions in here for these two things that we don't usually see, like not previously. So let's take a moment to go off to the side and think about a couple of things. So she's selling 440 donuts a day, and she's selling them for 50 cents per donut. But we are going to fluctuate the price. She's saying, well, maybe if I increase the price by 10 cents, and she figures she'll sell 40 fewer donuts, how much can we crank up the price to increase our revenue before we start losing money to customers not stopping by? What's that sweet spot there? So the selling price is being cranked up. It's not fixed. So let's create a formula for how this selling price is going to be changing. So we're going to let X be not the number of donuts. X is going to represent the number of times she has increased the price. Number of times we increase price by 10 cents. Number of times. X is the number of times we increase the price by 10 cents. That's the number of price increases that we might have. So if X is the number of price increases, then the selling price, it starts out at 50 cents, which we're going to write as $0.5. 50 cents is $0.5. 50 cents plus 10 cents for every time that she increases the price. So selling price is going to start out at 50 cents, but add 10 cents for each time that they crank up the price. So we're going to end up having to find how the X, which is the number of price increases that we would need by 10 cents. If that's the selling price, then the number of donuts that are being sold, she starts off with, she says she can sell 440 donuts at their current price, 440. But each time that she increases the price, we lose customers. So that's fewer donuts. That means it's going to be subtracted. And how many fewer donuts are getting lost? 40 for each time that she increases the price. So if you let X represents the number of price increases, then the price would start out at 50 cents and adds 10 cents for every price increase. And the number of donuts you sell decreases by 40 for each price increase. So these are the formulas that we're going to have to use when we're putting in the selling price and the number of items in our revenue function. So selling price is not fixed. It's 50 cents plus 10 cents. So maybe write that 0.10 X times 440 minus 40 X items. Now this is a classic binomial times a binomial, 1, 2 times 1, 2. So you'll want to FOIL this, distribute it, and collect like terms. We ultimately want a nice revenue function. So let's take this 0.50 and multiply it by the 440 and the 40x. I get 0.5 times 440 is 220. I'm going to take 0.5 times 40x is 20. So I have minus 20x there. Now I'm going to take this 10x or 0.10x because it's a decimal, 0.10x, and multiply it by 440 and 40. So 0.10x times 440. 0.10 times 440 is 44, but I have an x next to it. So that should be 44x. And then 0.10x times 40x is 4. So I have a positive times a negative, which is negative. 0.10x times minus 40x is minus 4x squared. X times x is x squared. Minus 40 times 0.10 is minus 4. So we get there. Let's collect like terms real quick. I have minus 20x plus 44x. The revenue function itself is 220 plus 24x minus 4x squared. I now wanted to maximize revenue, right? I wanted to find a maximum of this. So what we should do then is take the derivative of this and set it equal to 0 so I can find the critical number. Derivative of 220 is 0. The derivative of 24x is 24. The derivative of that is a power rule, minus 8x. Now I'm going to take this and set it equal to 0. I need to find a critical number that corresponds to a maximum. We have 24 minus 8x set equal to that 0. Add the 8x, divide by 8. You get x is 3. Now this isn't x equal 3 items. This is x equal 3 price increases, right? Because x represents the number of times we up the price by 10 cents. So if we have 3 price increases corresponds to the maximum, then what is the price of the donut? So the donut price starts out at 50 cents, and we just up the price by 10 cents 3 times. So the donut price should be the 50 cents plus the 10 cents added 3 times. So you end up with 50 cents plus 30 cents, which is 80 cents for my donut. So the new price per donut is 80 cents, or $0.80. So I'll put $0.80 here, which is 80 cents. Okay, so that's the price. And then it says, what is that revenue then? So if this is the price of the donut, and we had 3 price increases maximize revenue, if I wanted to know what the actual revenue itself was, you take x equals 3 and put that into the revenue function. So find R of 3. Plug 3 in here. This gives you 256 when you punch it out on your calculator. Now that's $256. So the first part of the question asks, what's the price per the donut? Well, then the price per donut is 80 cents or $0.80. With that many price increases, 3, we find that the revenue is $256. Make sure you're plugging in the X value of 3, not the donut price value. And we get 256 here. That's our revenue. Okay, last one, but it's very similar. We want to maximize revenue. It says a furniture store sells 224 coffee tables per month at $1,400 each. The owners estimate that for each $100 increase in price, they will sell 7 fewer coffee tables per month. Find the price per coffee table that will maximize revenue. Now, when they say maximize revenue, that means that they want me to find a critical number of the revenue function, which means that I need to build the revenue function somehow. And the revenue function is always given by the selling price times the number of items. We just might have different formulas for what those are. And that will be the case this time because my selling price, it looks like it's not going to be fixed. It says we sell the coffee tables at $1,400 per month, but we're thinking about increasing the price. So we're going to have an expression here for how the selling price is supposed to change. The number of items, it says, well, each time that we increase the price, we sell 7 fewer tables. So the number of items will change as well, depending on what the price is. So the fact we have to come off to the side a little bit and discuss what would be the equation for selling price and what would be the equation for the number of items. So the variable here is how many times they increase the price. So we don't know what the price is going to be because we don't know how much they increase the price. So what we're going to do is let X represent the number of times they increase the price by $100. So if X is the number of price increases by 100, but the number of price increases, then what does that mean happens to the selling price? Well, the selling price starts at $1,400, and we are going to increase the price, so that means they have a plus sign there, increase the price by $100 for each time that they saw fit to increase the price, which is X. $100 per price increase, where X is the number of price increases. So if that's the formula for the selling price, then how many items will be sold? The number of items will also change in a formulaic way. It says that they usually sell 224 coffee tables at that flat rate, but if we increase the price, we will sell 7 fewer. So our number of items starts at 224, but each time they increase the price, the number of ones they sell goes down. So we have a big minus sign here. Minus, how many fewer do they lose? 7 fewer for each time X that they increase the price. So let's take these values and plug them in for my revenue function. Revenue is the selling price times the number of coffee tables sold and I'm supposed to maximize that. And what do they want me to find? They want me to find the price, the magic number on that coffee table that will maximize revenue. So let's figure out the price. X is the number of times we increase the price. So in helping me find how many times we increase the price, that'll let me know what's the price of my coffee table. So here's my revenue function. And in order to make use of this, we've got to simplify things here and combine like terms, have a nice workable function for R. So let's take this 1,400 and multiply it by 224 and minus 7x. So 1,400 times 224, 313,600. And I have 1,400 times minus 7x, which is minus 9,800x. Then I have 100x times 224, which is 22,400x. And then I have 100x times minus 7x, which is minus 700x squared. That's my revenue function. Let's combine like terms in the middle. Minus 9,800x plus 22,400x. Is 12,600. So my revenue function is this. There we go. And I'm supposed to maximize that, okay. We want to maximize revenue, which means we need to take the derivative of revenue. The derivative of 313,600 is 0. The derivative of 12,600 is 12,600. The derivative of this is a power rule. So we have minus 700 times 2, which is 1,400, x to the 2 minus 1. Now I have to take this and set it equal to 0 and solve for x. So I add this term to the other side and I get here. Divide both sides by 1,400. Is 9. So that means x is 9. Now this isn't the price or the number of items. Remember, x represents the number of times they've increased the price. So they increase the price by $100 9 times. And that will maximize revenue while not. So that's the sweet spot between the maximum they can sell it and without losing too many customers. So they increased the price 9 times, each by $100 each time. So what is the new price of the coffee table? Well, the coffee table starts at $1,400 and they add $100 9 times, 9 price increases of 100. So we have 1,400 plus 900, which is $2,300. So this is the new selling price of the coffee table that will maximize the revenue. All right, that is it for this section. We are done. I will see you next time.